Well, alright. I'm, looking at this gosh dang old circuit. I drew it in OneNote for you all to see. Uh, Honestly, I kind of got bored. This was a homework problem that I'm trying to figure out. The problem doesn't even matter anymore because here's the story, right? This was a homework problem for a completely online class, right? And the website or whatnot, or whoever programmed the answer in for this particular question programmed it wrong, and which was verified by my professor, who then proceeded to show me the answer key, what it was supposed to be, and I was like, wow, I was right in the fact of that it was wrong in the way it was going about saying what the answer was. But the rest of it is the issue, where the part where it messed up, I understood. But then apparently the rest of the problem, I still would have done wrong and would have gotten it wrong. And I'm kind of upset about that. And I personally want to understand this circuit, so if you're in the mood to watch me try to get this circuit, I should probably have the answer key up somewhere. Probably. Maybe. Let's see, what do I got? I got a... I should probably blank out my screen for this. I gotta let's how do I do that? Can I just like, how do I do that? I don't know how to do that. What do I do for that? Look away. If I go to do I go to display real quick? How do I do this? Let's change. Yeah, you know what? You guys get to look at that for just a moment. That beautiful screen right there. Don't that look great? I gotta pull up the answer key. Let's see. What was it? There it is. Let me pull up that. I'm gonna copy and paste that. Let's see. Okay, there we go. That's what I'm looking for. Alright. Copy. Let's get that over here. Solution. Hey, I'll change my monitor back. There we go. And then I'll paste that right in there. I know this is gonna be super interesting, right? So we're gonna rename this. This is gonna be dumb doodoo circuit. Yeah, that's right. Okay. The dumb doodoo circuit that I'm going to I'm gonna look at right now, right? So, if you're interested, here is the problem. The point is that, or what was it? The idea is that this circuit right here, well, it's really hard to see my cursor, isn't it, when it's just a dot. Can I just, yeah, okay. Now that you can see that might be a little bit easier to see. So, what you got here is a circuit that I've been told has been in the A position. So you have a switch here. Like, look at this little straight line. It's in the A position for a very, very long time, right? All this means is that, or the important part, is that this capacitor over here is fully charged. Because the homework we're working with is like with time constants and looking at like RLC circuits a lot more in depth with like calculus. This isn't really calculus for this problem, thankfully, so this one's not too crazy to understand. It's more along the lines of just understanding time constants, understanding how to Thevenize, or I don't think this is proper terminology, but Nortonize a circuit. In this case, Thevenizing is the way we want to go, but the question is, let me use red. Let me change up the color here. So what you have is two things it wants you to find. There's the current through this 50 ohm resistor through this branch that they call I of t. So they're talking about a current over a certain time, hence the t. And then they also refer to this voltage over the capacitor in terms of time. The question is, well, I guess it's not really a question, they just tell you. You need to come up with two expressions that represent the voltage across the capacitor for all values of t, and same thing for the current through this 50 ohm resistor, also in terms of t. So let me undo those arrows real quick. There we go. So my plan is, if I can figure out, yeah, there we go. I wanted to scroll down more so I could just keep going down. All right, that'll make my life easier. Oh, okay, well this worked for whatever reason. I'm going to see what I can do about simplifying the circuit, because, oh, let me look at the solution real quick here. The part that bothered me was that this Thevenin voltage right here. I'm not sure how they got that, but that would have helped me get a lot closer to the answer than than before I started. I don't know how to say it other than I don't know how they got this Thevenin voltage, and that's what I'm gonna do now so I can get this off my mind. And if you want to stay and watch, that'd be great. I'd love to have some company while I try to solve this. So gosh, I need an actual calculator. I might not be using a on-screen calculator, or I can try to, but I'm gonna grab my TI Inspire real quick here. And if you're wondering why I'm doing this on YouTube, well, I really like electronics. I like math, I like circuits. This is the kind of stuff, for whatever reason, I just so happened to take to. And I really want to understand this, otherwise this is going to bother the heck out of me. So. Oh, I didn't know I had these OBS options for chat. That's cool. Put a little heart in chat. Oh no, can I not see the chat? Oh no. I gotta. Next. I need to choose Oh no, no. That's not the chat I want. That's not the email. No, come on, I gotta see the chat. Why? It's not Gmail, is it? No, it's not Gmail. Who uses Gmail? Is that good? I don't know. No. No. That's not my shit. What? Oh. Is that good? Oh, that works. I don't know. No, it's not. Wait, why am I logged into YouTube through the OBS chat? That's not my shit. No. Stop that. It pulled up a live video. Look at this. Look, I'm trying to be in my OBS chat, and it pulls up this. I've got one viewer. Yeah, it's me. Great. How do I... What? In this case... Oh. Okay, I am live right now. Alright. Or is this my... Oh no. Wait, am I live right now? What? Am I live? I'm live right now. I'm live. I'm alive. You got my stream. Got a video, audio, acceptor, villager. Well, that'll have to do. Alright, we're back. Here's the idea. So, again, this circuit, gotta find an expression for the voltage over the capacitor in terms, for all values of T, and the current through this 50 ohm resistor for all values of T. And, the biggest thing is trying to Thevenize this. Ugh. Alright, so... But I want to understand this. this circuit. Okay. So... the thing that I want to personally understand is how in the heck they got their answer. The answer in question is this solution right over here. So they had this Thevenin voltage of 4.9979, but that didn't make sense to me the first time I was looking at this circuit. But I'm going to try to Thevenize it right now and try to make sense of the 4.9979. But I thought I'd do it on YouTube, just so I would have friends. Okay, I would have company. I mean, if you want to be my friend, that's okay too. I'm not going to say no. If you want to be, you can stay. Hate your life with me trying to Thevenize this thing. It's fun to me. I, for whatever reason, like math, and I like this stuff, especially with circuits. So I want to know this voltage here, right before this switch flips down to B. So we're looking at what is the voltage here at t less than 0. So to do that, in my mind, I'd be thinking, okay, if the switch is at A, what you have is this part of the circuit. I mean, there is a complete circuit right here, so there is something happening here, but I'm more concerned about this capacitor and what the voltage here is doing. So in my mind, I'd be thinking that you have 10 volts in series with a 5k ohm resistor. This travels along this node and skips past this. This is not connected at all before t equals 0, so this connects along here. So you have a 5k in series with a 20k and a 2 microfarad capacitor that are in parallel with each other. So you have a voltage divider. And because this has been on for so long, we assume that the capacitor is fully charged, and a capacitor in a DC circuit is a short. So basically, there is 0 current, theoretically, or ideally, flowing through here, and it's all only going this way. How do I undo that? Can I just do Control Z? I can do Control Z. There we go. Okay. Is there a way to easily just, like... I want to keep full screen for reasons. Mainly because... how do I... What? Hold on. How do I do this? Why? Oh, okay. No, please. What? Please stop. Please, no. No. Exit? Okay, go to here. Where's my display? Display capture. Give me 1 sec here. You get to look at whatever the heck that is. I don't know what that is. Can I... No, that's not what I want this to stay pinned. But can I have that stay pinned? Oh, wow. You can't, can you? Oh, that's not really what I was going for, but... What? I didn't know you could do that. Interesting. That's kind of crazy. Oh, and, yeah. Alright, let's keep going. That didn't help, but okay, let's do that. So, take off that. If that's the case, then I'll pull my eraser real quick here. Take this off. What I do know is that just by inspection, if you have a 5K and a 20K ohm resistors in a series like that, you have a voltage divider. So 5K plus 20K equals 25K. And if you want the voltage at this point, you have to do voltage divider math, which would be 10 volts times 20K over 25K, which is the same as saying 10 volts times 4/5, which equals 8 volts. So, I grab my eraser, do that real quick, grab my red. The voltage here at t equals 0 equals 8 volts. There we go. So then, next would be something, or I pointed out earlier, was that this section of the circuit is still a complete circuit right there. There is current flowing through there, even though it's not connected to this part of the circuit through that, because of that switch there. So you have another voltage divider here, and if you look at this voltage right here, what is that? You have 9 volts into a voltage divider of 10 ohms and 50 ohms. So it's, what is that? 10 plus 50 is 60. And the majority of the voltage is going to be across this 50 ohm resistor here. What is that? So you take, what is that? It's going to be 90 times 5/6, because it's going to be 9 volts times 50 divided by the total of 60 ohms, which is going to be 7.5 volts. Now, this part's going to be interesting, because if I look at the solution, this is the part that kind of confuses me about their solutions here, because they, for whatever reason, get a Thevenin voltage of 4.9979 volts. I'm not sure how they get that, to be honest, because here's the thing. In my mind, they, from what I read from the book, and of course this is what I'm going to be trying to figure out, hopefully why I'm wrong or why they're wrong. And the point is, you have this, what is that? You have this formula that's going to be the basis for how we're going to get this expression, right? So you have the voltage. Oh, let me write it out first, and then I'll explain what this is. So this is, how do I want to write this in a way I can easily explain? Let's see. I'm gonna call this V2. No. I can just call it V minus V0 e to the negative t divided by that. Okay, so what this is a formula that's talking about the rise time or fall time, however you want to refer to it, of a capacitor. And this formula represents specifically the change in voltage over the capacitor over a certain amount of time. And now in this case specifically, this one is for, what is that? That's for when voltage is decreasing. Or is it? Yes. And that's, yeah, I was trying to remember that. It's this one is for when voltage over a capacitor is decreasing, and there, of course, is one for it increasing as well. That's, what is that? V of t equals V plus, everything is very similar, except for you have 1 minus e to the negative t divided by t. Like that. This one is for the voltage over a capacitor going up. And I should probably specify this voltage as being something different. Let's go... maybe... it'd make more sense, I think, to switch around this. I'm being a little picky with this because I want this to be correct. Oh, no, hold on. I had that right, I think. The top one is the one that I want to change. You have your initial minus your final. The reason I chose that is so I keep this and this, well, not, or this quantity, or these quantities, positive at the end. That's what they're going to be. But the idea is that you have the voltage that the capacitor is going to drop down to here. You have this side of the equation, yeah, so you have, that's the final voltage that it's going to be after a certain amount of time. This section here represents the change in voltage over time. So basically at t here, at this t, not this t, this is a different t. How do I redo? That's not how you do that. Anyways, I'll just do that. It is kind of hard to differentiate that, isn't it? What if I use more colors? That's the voltage you're going down to. This is the voltage change. This is the change in voltage over time. This voltage right here is the difference between your starting voltage, where the voltage that the capacitor is at initially, minus the voltage it's going down to. Because, like, if, let's say, what is that? Over here, you have, at t less than 0, you have, what is that? 8 volts here, and down here you have 7.5 volts. When this switch connects to here instead, now the 7.5 volts and the 8 volts share a node, and what that means is that, well, this capacitor here is, its voltage is going to go down. The reason being is that because this 10 volt source over here is no longer charging it up, we only have a 9 volt source now that's charging it up. But at most, this 9 volt, I know there's a lot of arrows, this 9 volt source down here is only going to be able to charge that capacitor up so much. Now, you might notice that when this circuit now comes into play, or was it, now that we have almost a new circuit here because of the switch changing, because we have one voltage source, this 9-volt source, here, what is that? How do we calculate what the voltage at this node is going to be? Well, we have a 9-volt source. I'm going to erase all these arrows because I think I made my point clear here. So I know what we're looking at now. The fun part about this is that we now have a new circuit, and I could redraw this too. I could redraw this as a different circuit now that this section no longer plays a role and we are only looking at this section, the green section. We have a lovely new circuit. This is where things get interesting. So, well, at least for me, because I really want to understand what's going on here. So, I want to be able to feel like I can get that same Thevenin voltage that they're getting in their answer here. I think I've already said that, but doesn't hurt to reiterate. Nah, that's not. It doesn't hurt to say things over again to help me memorize some certain things. So we want to know how they get this 4.9979 volts. Because from my point of view, I don't see how they can get that. In my mind, anyways. I don't know yet. But I'm gonna see what I can do. Oh, right. Because if I look at their solution, if you look at this, if you look at this one right here, that's the expression they say should represent the voltage change of the capacitor after the switch changes at t equals 0. Now, this is weird to me because they say that essentially the final voltage that it's going to is 5 volts, which, I don't know, that doesn't make any sense to me because why would it? I feel like I'm missing something really important here, and the fact that we have a difference of, or was it this 3 volts here, makes me believe that at some point, maybe they think that the voltage is supposed to be going down to 5 volts for some reason. Because maybe the 3 does make sense to a degree. I think that makes sense in my head because if you take this section here, right, if V0 minus VF equals 3, and the final voltage they're thinking is 5, then V0 would have to be 8 volts. That makes total sense to me, for sure. But so they do agree then that the that the starting voltage is 8 volts, which is what I just got done saying is right here. So that's good. I think that's good. But they, for whatever reason, think that the voltage is going down to 5 volts instead of 7.5 right here. So I'm going to redraw this circuit using, I'll go back to black here. Let's see. So what we have now, strictly speaking, with our new circuit, we have this, we have a resistor like this and a capacitor. There we go. Perfect. This side we have 9 volts. We have 10 ohms, 50 ohms, 20k ohm resistor, and a 2 microfarad capacitor. There we go. Now, the fun part is, let me look at the fact that we have, at t equals 0, we have plus or minus, what do we got? There's 8 volts here at t equal to 0. But what I was expecting it to go down to was 7.5 volts. Which makes sense to me. So I'm wondering if the rest of the problem is just wrong. But I was going to try to Thevenize this circuit. And the way that I was going to do that was you essentially, what is that? You take out the load, and then you want to see what the voltage would be at this point from here to here. What is that voltage going to look like? So what we do is, oh, I guess that does make sense. We'd have, well, no, you have a 10 ohm in series with the 50 in the 20k when they're in parallel. Okay, so let's redraw this one more time. Down here, we'd have $9 volt. We'd have a, I'm going to draw that as my 10 ohm. $9 volt, 10 ohm capacitor. Oh, whoops. That's not going to be 20k. That's 20k in parallel with 50 ohms. So let's do 20k to the negative first plus 50 to the negative first to the negative first. When resistors are in parallel, this is a way that you can solve for what their equivalent resistance would be is if they were one resistor. So if you do solve for that, because 20k is so big, it's going to be just a little under 50, like 49 ohms. So 50 to the negative first. You get about 49. .875. Yeah, not a big change at all. ohms right here. And if we simplify it one more time, I know I drew the capacitor in there. I guess that's technically not correct. We really see a we see the spot where a load of some kind would be. I have a different way I'm going to go about this, but I'm going to continue on assuming the capacitor is the load for right now. So let's see. If I keep going, I now want to add the 49.875 ohm resistor and the 10 ohm resistor together, and I get 9 volts. With 59.875 ohms. Did I do that wrong? I feel like no, yeah, I think I went one step too far. Oh yeah, okay, yeah, that's right. Hold on. I was doing something else in my head. So we have here a 10 ohm and a 49.875 ohm resistor in series. We want to know the voltage here based on that resistor. Okay. To figure that out, that is, again, one more voltage divider. We do 9 times 49.88 ohms. I'm rounding just to make room here. Right, we do add these together, so it's still like this. I'm going to calculate using the real values. Yeah, because the real value, if you're wondering, of the 49 point something odd ohm resistor is like 49.8753117200698. And that's, my calculator can only go so high in terms of decimal places, unless I try to set it to something higher, which I don't know if I even can. So we're going to go with it. So we add 10. So 59.8753. 49 divided by the 59 gives me about 0.833. I multiply that by 9, and I get just about a little under 7.5 this time. So this is going to be 7.497 volts. That voltage there tells me what that voltage is going to be without the capacitor on the other end. But that's the thing, right? When you think about how a capacitor works, it's going to what is that? If it has a voltage across it greater than what the voltage source is, it's going to discharge until it reaches a point that the voltage source charges it with a voltage greater than what it can discharge, if that makes sense. if you don't know electronics that well, but I'm just reiterating stuff that I know. You probably already know this if you're watching this video. Or might not, and if that is the case, then that's awesome. Alright, cool. Then I might be able to teach somebody something, which sounds actually really cool to me. Alright, so next part is, that's what I'm saying is the Thevenin voltage, but is that right though? So now I did that in terms of this being a voltage source. Maybe they treated this capacitor like a voltage source as well. But that doesn't sit right with me. I don't know how I still don't understand it. Because they're saying it's going to go down to 5 volts. But you have a voltage source that can put a greater voltage there. That is strange to me. Let me look at their solution one more time. Let's look. Because this is also from a book that does not really explain this stuff well. They say, when the flip is switched, we have a Thevenin equivalent circuit with a current of 0.6 amps through R10. They're saying something about 25 thirds, which I'm not sure where they're getting that. What is 25 thirds? 8.3333 something ohms. Okay. Out of curiosity, what is this? Okay, yeah, no, that doesn't tell me anything. Never mind. Just some thoughts to myself. Where would they get 4.9979? So they're thinking that we're going to be seeing 5 volts. So let me look at the other numbers in this circuit, right? What if by chance they thought this 10 ohm and the 50 ohm maybe have gotten switched? I'm not sure. So what would that look like? I'd be thinking then that I gotta do another voltage divider where I'm thinking I'm gonna explore that. So let's see. Let's say we have maybe they thought the 9 volt yeah, so let's say if we had a 9 volt, what if they got this one and this one switched up? What would that look like in terms of a voltage right here? What is, let's see, 20k, 20k to the negative first plus 10 to the negative first to the negative first. You get about 10 ohms, really close. It's like 9.99 ohms. So this voltage here is going to be about 1/6 of 9. What is that? 9 times not 1/3, 1/6. Oh, whoops, I did 9 divided by. 9 times 1 divided by 6. Or about 1.5 volts. Which isn't what we're looking for. Okay, let's scribble that out. Okay. What other possibilities were they thinking could have led us to 5 volts here? This is so messy. Okay, we can erase some of these lines and hopefully make this easier to look at. Okay, so why would they think that's about 5 volts roughly? Let's think. So 5 volts in terms of 9 volts. Is there a ratio of these resistors that would give us 5/9? What would that be? Is that a possible? What is, honestly, what is 50 in parallel with 10? Yeah, oh yeah, I was saying about 8.33 something ohms. Yeah, nothing crazy. Because if we have a 20K in there, yeah, why do they think that's 5 volts when it's clearly going to be 7.5 there? Because I'm already assuming they're wrong, and the voltage we would end up seeing is not going to be 5 volts. It's going to be 7.5. So I might just be doing this for nothing, but it's nice to know that I'm thinking it through as best as I can anyways. And if anybody can see why they might think it's 5 volts there, or 4.9979 to be more accurate, I'd love to know. That one's just a little tricky for me, and I'm not sure why. Because after I'd simplified it down, the voltage across the capacitor, across the load, is going to be determined by this 49.875 ohm resistor. Now, the other thing, though, is to look at Thevenin resistance. Can we get the same? And the way we would do that is we essentially cross out this voltage source and we make it a short from here to here. What that'll look like to start with is, let's draw a straight line that way. I like doing lines like that to divide up my work, even when I take notes and whatnot. Yeah, it just helps me. I do more of like a little wavy line in my notebook. I don't know why. That feels better to me to do a wavy line. But what was I saying? Okay, so now if we short out the 9 volt source, what you have really over here is 10 ohms. Like this. 50 ohms. And your load here, so you have 10, 50, 20K, 2 micro. We want to look at the resistance that way. The way we would do that, right, is we would take 10 ohms, right? We would take yeah. Okay, use a different color here. Let's see. We have 10 to the negative first plus 50 to the negative first to the negative first. I said that equals about 8.333 ohms. It's 8.33 repeating. If you take 8.33 to the negative first plus 20K to the negative first. What is that? So take this value, negative first plus, 20K, there we go, to the negative first. And we get 8.329. Whoa. That is the worst 8 I've drawn yet. It's hard drawing on a computer. I'm not used to doing this, but 8.3299 ohms. And that looks really similar to what they got here. Yeah, look at that. So from what I can see, I was able to do that right, but am I doing the voltage wrong? So, let's go. Yeah, you know what? Let's go online here. There's me using Desmos. How to find Thevenin voltage. Thevenin theorem. Circuit bread's always, I think, pretty good. Let's look. So, yep, we end up with Thevenin. We start with like maybe some circuit kind of like this, and we want to simplify it down to something that looks like that, which is, yeah. So they say, review your circuit, identify your load and the nodes it is connected to, and then you move the load resistor. Now see, that's an interesting thing. The other thing I forgot to try was I wanted to check the fact that they're looking, that even though they were looking for the voltage across this capacitor, they're looking for an expression to represent that. They're also looking for, they're also looking for I of t based on this 50 ohm resistor. With that in mind, I would say let's try looking at it from that point of view. What if the actual load instead was the 50 ohm resistor? I think that's a reasonable way to go about it. So what we have, I would say, we have our 9 volts. Again, for the 10 billionth time. We have a 10 ohm resistor that would normally be in parallel with a 50 ohm resistor there. You have 10. Then you would have 20. And your 2 microfarad capacitor. Now, what I see here though is interesting, to say the least, because if I were to try to think like what voltage would be here, it's already simplified enough to the point where we have a voltage divider between the 20K and the 10 ohm resistor, which, because 20K is so much bigger than 10 ohms, we could practically say the load would have almost the full 9 volts across it. It's going to be, like, if I did the 10 ohm and the 20K in series, that's 20K divided by, well, 20,010 times 9 is 8.9955 volts. Such a minuscule difference, it don't matter. So obviously, they're not getting 5 volts from that. Oh boy. Oh, jeez. Ain't that interesting? What is that? Neither of what I was thinking is right. Okay. Yeah, I have no idea how they got that. That is, ugh. Okay. So, t equals 0, right? At t equals 0, they said that this switch flips down from A to B. Now, this switch here, they specified drawing it that way because that is a symbol for a specific type of switch called a make or break switch. A make or break switch, what it does is, as it switches down, you have this little tiny section that I copied because I don't know if it actually really matters or whatnot, but what we have is that we have like a specific period of time, like a little tiny bit, where both, what is that? Where this section here and this section are connected. I'm gonna erase that, don't worry. But that's only for like a fraction of a second, you know? For somebody, I mean, realistically, you imagine somebody flipping this switch, they're not gonna leave it, they're not gonna, flip a switch and leave it in the middle. But maybe they thought, for whatever reason, maybe they accidentally left this 5K in their explanation for trying to find a Thevenin voltage, because they obviously did the rest of it right. They found the... I was able to find their Thevenin resistance, so I agreed with what they did. But how did they get the voltage? That's my thing, right? Now... yeah, how did they get that? How would they accidentally maybe throw in that 5K? Maybe they were just tired when they did this one. I don't know. How would that look? How would that 5K come into play at any point, right? Maybe they were like, oh, well, yeah, the 10 volt source doesn't put a have anything to do with this. What is 20K in just for kicks? What is 20K in parallel with 5K? 4K. Okay. What is... wait, let me think. What is 4K in parallel with the 50 ohms? It's not much different. Let's just say that. Than the original 49.88 something. It's now 49.38. Yeah, that does not put us anywhere near 5 volts. Yeah, so that's interesting, right? So let me look at the... did I write down the voltage that I got? I got about 7.497, right? Was that... or did I round that? Pretty sure I rounded that. What did I say specifically? I said 7.49688. But it doesn't look anything similar to 4.9979, and of course it doesn't, but I'm referring to the decimal places. I was trying to imagine, like, what if you took that minus, like, 2.5? What would that look like? Actually, look at that. No. Okay. That's an interesting thought. If you take... let's see, can I scroll... I can scroll over on this. That's kind of... I think that's kind of silly. Let's draw a line. Maybe I'll get some extra... yeah. If you take... you know what? That's bothering me. I'm gonna erase that. Why am I getting notifications on my phone right now? Whatever. Okay, here we go. I would say that... oh yeah, if you take about, what is it, 7... I'll use a different color. Let's do blue. 7.49688, and you minus 2.5, you get about 4.99688, and they were getting about 4.9979. I know that's not really that close, but I guess if you did round this up, you would get 4.997. I don't know how they would, I don't know how they get that. I don't think that's right. Because the point of this equation down here is to represent the change in voltage over the capacitor specifically. And I also threw this into LT Spice, thinking that this would, help me get to that same answer. It doesn't. It does not give me the same answer. It gives me my answer of 7.5 volts. But, yep, this just leads me to believe that they were still wrong even with the Thevenin voltage. I don't know how they got that. I still don't know how they got that. when the switch is flipped, we have a Thevenin circuit with those values. Now, they say that, but okay, now let's look at the currents, right? They're saying, I think they're trying to say that we have 0.6 amps through the 10 ohm resistor and 0.6 amps through R equals 25 divided by 3. 25 divided by 3 is 8.33. Oh, hold on. What was the... there was something that I calculated just a bit ago that got me 8.33. What was that? Oh, yeah, the 50 ohm and the 10 ohm in parallel. That's interesting. Okay, so let's look back at that. Oh, I gotta go back, yeah. To the dum-dum doodoo circuit. I'm going to erase some stuff here to make this a little nicer to look at. Let's see. Okay, so what is the... I'm gonna go all the way down on my calculator here. What are those 3 resistors in... Oh, I'm sorry, no. The 20K plus the... Or what is it? The 20K and the 50 ohm in parallel. Then that's going to be in series with the 10 ohms. And if I take 9 divided by the answer, we get, or I'm getting 150 milliamps. So they said there was like 0.6 amps going through that 10 ohm resistor. So if you take 0.6 times 10, they're saying there's about like 6 volts across that 10 ohms. But why would they think that, right? Why would they think there's 6 volts across there? The remaining voltage would have to be 3 volts. Maybe they thought the 20K was just 20. Let me look at it like that. So what is 50 in parallel with 20? We'd get like 14.28 ohms. What is, now I have an idea. What is that 14 divided by that times 9? That's closer to that 5 volts I was thinking. But, or they were saying, but I'm getting 5.294 volts, so that's not the same. So that's definitely not what they were thinking. So that is an interesting question. Why would they say there's... they're saying that with their Thevenin equivalent circuit, they're getting 0.6 amps. Okay, so let me take 9 volts then, divided by 0.6 amps, 15 ohms. Okay, so where did they get 25? Yeah, wow, I don't know where they would have gotten 25 thirds. Unless they thought the 9 volts was, unless they thought the 10 ohms and the 50 ohms was in parallel for whatever reason. Okay. Let's see. How could we possibly get 15 ohms out of that. Yeah, that's kind of crazy, ain't it? They think the Thevenin voltage is 4.9979. So I'm assuming that's what they're trying to say. I'm assuming they mean that I'm assuming what they're trying to say is that there's 0.6 amps through the 10 ohm resistor, but then they're saying 0.6 amps and a resistance of 25 thirds. Okay. Oh, let me look at it like that. What is no, because 9 divided by 8.33 isn't going to be anything. There's got to be something that they thought of that would have made sense to them for thinking that the resistance was 15 ohms. Did they accidentally add, like... No, okay. They didn't add those together. Yeah. I'm kind of at a loss. This one's definitely strange. Now, don't get me wrong, they... Oh, wow. Yeah, I don't know. That's a tough one. Wonder why that would have... Well, I wonder why they would have thought that. And that's the stuff that makes me curious, you know? Some ways that people think about some of these problems and whatnot, I'm like, how did they how did they go about doing this? And that's what I find fun. The time constant was something that I did get right, the 16.66 microseconds, and I'm trying to remember specifically how I did that. Oh, right. So it was that Thevenin equivalent resistance, yep. So when you get that, I think do I still have that circuit drawn? Yeah, kind of. Basically, if you want to know about how you would find the that time constant there, I'm going to erase. My voice kind of peaked there for a second. That was kind of funny. This was what? Oh no! Oops. Whoa! What? Whoa! Why did I do that? Okay, that was weird. 8.33 ohms, and can we not erase my whole circuit, please? Two microfarads. The voltage across this capacitor is going to charge at a rate based on its time constant. So, which is going to be the resistance it sees it relative to itself, and when we have a Thevenized circuit, it makes the solution much easier because there's only one resistance in this circuit right now, which is that 8.33 ohms. That was the R value times our capacitance gives you 16.66 microseconds. And it's that easy for that time constant value. I know how they got it now, and I'm just like, these two make sense, but that doesn't. Why though? Why do they think that? Now, what if they, so now here's a question. If they say 5 volts, there's to some extent some mistake on their part for thinking what maybe this voltage was. It definitely wasn't 10K because then their answer would have been more than 5 volts. So they, for whatever reason, I'm guessing, thought that voltage was less. So, gosh, okay, so we have to have some voltage equivalent to, let's say they got all the resistors correct and the like, so like they knew all that, but for some reason they had a different voltage in their head. And to figure out maybe what that was, we'd have to think about the, I don't know, we'll use approximately 5 volts. For whatever reason, they say 5 volts equals some voltage times the ratio of that 49 point, what was it? I wrote it up here, didn't I? Oh yeah, 49.875. Divided by 59.875 ohms, the 10 ohms more. So V then, if I calculate that out, that's going to be 5 volts times, I'm going to use the real value in my calculator. Yeah, there we go. What is that? Okay. And then we divide by 49.875. Six. So for whatever reason, they must have been thinking 6 volts. Now, that's an interesting thought too, because maybe they saw 9. This might be funny, but sometimes people do some silly stuff where maybe they saw that 9 and just said 6 in their mind. I wouldn't know why. There's no 6 in here. Maybe somebody, well, now let me specify this. This homework problem where this voltage source here is relevant, that voltage source is different for each student that does this problem. Now the only thing though is my voltage source was 9 volts, not 6 volts. They also ended up switching these two voltage sources in their explanation for how I would have, or for how I should have solved mine, which my professor agreed, and he knows that the question was was programmed incorrectly in the book. It's just kind of silly. It just makes me wonder, how did they get there, you know? How did they, for whatever reason, I think they started specifically with 6 volts, because look at this voltage, right? The fact that this voltage here was where it was specifically. They're saying approximately. Now, let's say I use their... Maybe I try to do this as 4.9979 times... What is that? 59.875 divided by 49.875. And you get almost 6. Almost 6 right on the dot. 5.99998521303326. The point is, it is either way. If you use 5 volts or their 4.9979, you get 6 volts. So what I'm thinking is, maybe they were looking at another instance of the problem. Maybe somehow for maybe mine in particular, maybe they somehow programmed it really wrong. So I don't know how they did it. But the later part of it, yeah, definitely does not give you a Thevenin voltage of 4.9979. I don't know if this is actually going to get on YouTube or not, because I haven't been recording, but if it does, well, leave a comment. Please. If you think I'm a dum-dum instead of this circuit. Because I'd love to know how they would have gotten to that answer. Actually, I wonder if I... Let's think. I was almost considering putting it into like Chat GPT or some kind of AI and seeing what it thinks. But I did do a circuit simulation software, and the circuit simulating software agrees with me, which I could do, but honestly, I don't feel like it right now. Oh boy, this has made me tired, and I think I'm done with it. I think I got out what I wanted to do for it. So, thank you for watching. Yay.